So decision trees are actually really easy to understand. What's sort of surprising is how well they work. So here we make a data set. And downloading a data set, this is another famous machine learning data set. There are some flowers, and they fall into three categories. Setosa, versicolor, and virginica, they're irises. And they measured a few parameters of these things, the petal width and the petal length and a couple other parameters about these irises. And so there's only about 100 data points, and you can practice sorting them into categories. So here is what a decision tree does. And this is incredibly simple. It just takes one value and makes an if-then statement. So if the petal length is less than 2.45, it goes here, otherwise it goes there. If the petal width is less than 1.75, it goes here, if not, it goes there. So there's only two if statements, and that's the model. And the end result is you can rate the quality of this model by how well it purifies the data. So there's a concept called Gini impurity, which is pretty much like entropy, which measures how much variety there is in the data. The original data has 50 in each class, and they're all mixed together, so that's 66% impure. Then the first statement picks out all 50 of the setosas and nothing else. So this is perfectly sorted, so the Gini impurity is now 0. So that's good. We were able to totally catch those. The other two are harder to tell apart. Now we have 0, 50, 50, so the impurity is 50%. But this if statement sorts it into this group, which is 49 and 5 and 1 and 45. So it does most of the separation, but there's still some impurity left. And that's what you get with 2 layers of a decision tree. And so you can display the predictions. Here's the decision boundaries. The data is here, and the color tells you which category they're in. So the first if statement did this, which gave us 100% success on that pattern. It mixed these two together. The next one did this, and it did some separation, but not perfect separation between them. So now that's a decision tree with depth 2. It does 2 if statements. If you do depth 3, you get this. It's going to separate each of these again. And then you're going to get better data. So you can have higher depth and get more and more accurate. One great thing about decision trees is it's very easy to understand how they work. If you don't like what it's doing, it's actually just if statements. It's like old-fashioned code, so you could go change one of those if statements or add another one if you wanted to make it do something different. So it's interpretable. Now, you can do it to fit more complicated tasks. You could do curve fitting with decision trees, which may seem kind of insane, but you can do it. So here's the data we've seen before, x times cosine x plus some noise. Now I'm going to try and fitting that with a decision tree. So if you fit it with a decision tree, a depth 2, then it's going to do this, and we have squared error instead of impurity, so we're trying to make the squared error go down. So 0.19, go down to 0.15, go down to 0.03, so it's getting better, and here's the fit, which is pretty horrible, but what do you expect with 2 layers of if statements? It's like very coarse analog to digital conversion. So you need more depth. If you go to depth 6, it's getting better. And then you can have unlimited depth. You can let it go, and now you're going to get overfitting. Now it spikes every point with an if statement, so it's fit the noise perfectly. And like I say, this is where I mentioned before, human judgment comes in. Now, you could argue this is the most perfect solution. This is what fits your data. But intuitively, I feel like I really don't want this model. I'd even rather have this one, as more likely to actually generalize to be close to the real truth with more samples measured. This one, I don't think I gained anything from the last several layers of that decision tree. Instead, I just fooled myself into thinking it was better when in fact I was making it worse. So that's one decision tree. Now, by itself, it's pretty simple, but what's really powerful is forests. And this turns out to be the way to go. If you have different machine learning models, then you can average out the error by combining their outset. So here, we make one of these curved data sets with 2 curved things. We're trying to separate the green from the blue. And now we make 3 different models. We have a support vector machine, a random forest classifier, and another one called a logistic regressor. They're just different kinds of models. We're going to train those 3 models on the same data, and then we're going to take the output of them and combine them. And so the first one is voting. We're going to have each one of them vote on whether it's green or blue. And if you have at least 2 votes of green, we're going to call it green. You have 2 votes of blue, we're going to call it blue. So in that case, The three models by themselves have an accuracy of 86%, 89%, and 89%, but by combining all three, the accuracy goes up to 91%, which makes sense. They've hopefully made different errors, and the errors have tended to cancel out. But this, by the way, is pretty stupid, because remember, the models do not give a yes or no answer. They give an analog answer and a signal. And so just telling me you called it blue is not as good as giving me the strength of the blue signal. So if you take the soft voting, where you actually take the analog output of the models and then combine them, the soft voting classifier gets you up to 92%, because you're keeping more of the information that each model gave you about it. Now you can do bagging. You can make many random samples of the training set, different subsets, and train models on each of these different subsets of the training set, just trying to get independent models that are going to have independent errors that will tend to cancel out. And so you make a forest with 500 trees. You make 500 learning trees, because those are really fast to make. 500 decision trees trained on different subsets of the data, just to try to make them independent, and then you combine them together. And you can even use random decision trees, which is something that blew my mind. Instead of optimizing it at all, you just randomly pick a parameter and randomly pick the threshold for the if statement. Make a random decision tree, because that will tend to sort them into some kind of categories. And then you just combine a lot of them to optimize the output. And so here you get a single decision tree that overfits the data. But if you do 500 decision trees and combine them together, that actually fits the trend pretty well now. That's with bagging. And so here, you can do 5 trees and see how it goes. And now we can talk about some other techniques, like ADA boost. What you do in this one is you run a model, and the model tries to fit the data, and now you take the errors, and you have another model to put the error correction on that one, and another model to put the error correction on that one. So that's another way to do it. And so you can do this with 5 iterations of a vector machine model. And what's interesting here is you get to see the effective learning rate. So here, with a learning rate of 0.5, you get what you expect. It starts with a bad fit, and after you train it, it gets better and better until it converges on a pretty good fit. But if the learning rate is too high, then it takes big jumps in the parameters, goes past the good spot, goes into the bad spot, a different bad spot, a different bad spot, and just goes off the rails and goes crazy on you. So here's an example of 10 cycles. With the learning rate too high, it just jumps all over the place and goes crazy. With a slower learning rate, it actually converges on a nice, smooth fit through the data. So that's ensemble learning and random forests. It turns out the random forests are generally considered one of the most powerful machine learning models available. Even though they sound stupid, when you combine hundreds of them together, they're actually very good at fitting things and getting good fits. So let me stop this one.